Welcome back to the highlights from the mini symposia at PESC 25. I'm Erik Lindahl, and joining me here I have Drs. Nikola Kolonna and Yuri Timrov. You have organized the mini symposium on materials for energy, and not just any materials, but doing this with first principles, where computing is important. Tell me more about this. Why did you organize the symposium?
Well, when we started organizing this symposium, the idea was really to gather all together some of the leading experts in the field, essentially because we share the common perspective that materials are really key for a sustainable future, and in particular for transitioning out from fossil fuel to green energy, essentially. And you can do this in many different ways, and so we invited speakers to discuss different topics like CO2 captures or production of hydrogen out of novel catalyst material or photocatalytic water splitting.
So as an ignorant viewer here from the outside, why do we do this in computers today? But producing CO2, that's something you do in the lab, right? What's the role of computers?
Well, because you can actually, on a computer, explore many more possibilities. You build different materials and you simulate the properties of those materials before really going to the experimentalists and ask them to really check if this material is good or not. Because from an experimental point of view, exploring thousands of materials is unpractical and unfeasible, while on a computational side it is way more easy, and we can screen materials before passing them to experimental colleagues.
Yeah, so that makes a lot of sense. So tell me more about this symposium today. What did you learn? What is the main take-home message from it?
So the symposium was indeed very fantastic. I agree with Nikola. So we learned quite a lot of messages indeed. We understand that there is a lot of work to do because climate change is a big problem nowadays, it's really pressing, and our actions must be really fast. And in this respect, computational modeling is very, very powerful and useful, and Nikola already mentioned why. So we learned that we need to use state-of-the-art techniques to work in this direction. So like machine learning and artificial intelligence is one of the most powerful techniques nowadays to speed up our progress in this direction. Also, we need to keep working on the methods, advanced simulation methods, and software to enable these simulations in the best way. And also, of course, we rely on supercomputers like HPCs, in particular here in Switzerland, in Lugano, CSCS. So to do our calculations, we need powerful computers, because without them, we would not be able to use these computation expensive techniques.
Yeah, and Alf, Switzerland certainly has a very nice computer in place right now with Alps. So what is limiting you? What is the bottleneck? What is keeping you back from delivering all these advances? If there is anything we should deliver to you, what should that be?
So one of the challenges, and maybe Nikola can add some others, our software may be a bit not yet at the level that we can fully exploit the power of these latest architectures. In particular, here at CSCS, we have Alps supercomputer, which is extremely powerful, but our software is still not being able to run on such incredible architecture. So there is a lot of work to be done to adapt our software for this architecture, and we really work intensely, in particular thanks to PASC, that funds really researchers fully dedicated to work on the software. And among other things, maybe Nikola can add.
No, I totally agree with you. So I think we are very distant from a paradigm where scientists do everything. So actually, I think we need an intermediate figure that actually bridge our expertise or our idea that are scientific idea and make them really scaling well on powerful architecture like Alps.
That sounds like a great conclusion. Thank you so much for joining us, and thank you.
Thank you.
Thank you.